On September 14th, the interstellar visitor known as 3I/Atlas upended all expectations, flaring dramatically and unveiling a spectral green aura spanning 500,000 kilometers, loaded with carbon dioxide at 8 times the level of water. This abrupt intensification stunned seasoned sky watchers, sparking frenzy across online forums and professional networks alike. Right now, 3I/Atlas is speeding toward a near encounter with Mars, sporting a backward-pointing tail aimed sunward, even as leading telescopes go quiet. The nearer 3I/Atlas gets to the red planet, the more unnerving the spectacle grows. What sparked this aberrant celestial event? And why is vital information disappearing right when the enigma intensifies? The revelations question our grasp of the natural world, innovation, and concealment. Anomalies started emerging on the evening of September 7th. Data analysts, whether in Tokyo or Arizona, saw their real-time graphs veer wildly from projections. 3I/Atlas, anticipated to gain brightness in mere tenths of a magnitude weekly, surged by 1.6 magnitudes in under 72 hours. Initial unprocessed readings, time-stamped and shared by hobbyists such as Robert McNort and Kei Yoshimoto, clocked it at magnitude 10. For at 2,300 UTC, then dropped to 8 right before sunrise. Such a spike demands attention. It's an urgent alert. Soon after, the Comet OBS email group and Cloudy Nights discussions overflowed with new observations. Every data marker soared past the predicted line. What was meant to be a gentle ascent turned into a sheer cliff. A 1.6 magnitude leap implies the comet was abruptly scattering fourfold the illumination that simulations permitted. Imagine a low light suddenly blasted to maximum in the dead of night. A few speculated on an outburst, perhaps a burst of CO2 escaping via surface cracks. Others floated ideas of observational glitches, like aperture distortions, overestimating the coma, or confusing haze for a genuine burst. Yet the data poured in relentlessly. Each update defied established norms. For those charged moments, the tail was owned by the dedicated amateur observers burning the midnight oil. Their instant graph shares form the heartbeat of an international stargazing effort. No one could predict the following measurement, but all grasped the gravity. When the brightness pattern shatters expectations, the universe is signaling something beyond current vocabulary. The figures are jaw-dropping. By mid-September, 3I/Atlas, with a core no broader than 3 kilometers, and likely smaller, was expelling carbon dioxide at 129 kilograms per second. To put it in perspective, that's equivalent to a compact lorry's worth of solidified gas turning to vapor every 60 seconds from an object tinier than many urban green spaces. Hubble's clearest snapshots limit the icy heart to about 2.8 kilometers in width. Still, the surrounding coma, that foggy sheath of vapor and particles, has expanded beyond 700,000 kilometers across. That's almost double the Earth-Moon separation, all stemming from one frozen mote. This goes beyond mere dimensions. The composition itself bucks convention. Typical solar system comets stir to life steadily, powered by water ice vaporizing under gradual solar warmth. In this case, water plays second fiddle. The James Webb Space Telescope spectrum from August 6th exposed a carbon dioxide to water ratio of 8:1. That's not merely odd, it's unprecedented. At such ranges, inter-solar system comets usually favor water over carbon dioxide, frequently by 10 times or greater. 3I/Atlas flips that script. Carbon dioxide leads overwhelmingly, with water lagging and carbon monoxide a remote follower. The JWST researchers, headed by analyst Dr. Alizia Franzi, highlighted the oddity in preliminary reports. Their simulations foresaw a measured buildup of emissions as the comet neared the sun. But what unfolded was an unchecked hothouse effect, with carbon dioxide gushing freely long before water could mobilize. As Dr. Franzi put it, this is a comet powered by an entirely foreign propellant. The ramifications extend past makeup. Detailed views from earthbound networks and satellite instruments reveal the coma threaded with dusty plasma strands, slender formations extending tens of thousands of kilometers, writhing and evolving over mere hours. These differ from the even, widespread hazes of ordinary comets. Rather, They suggest unbalanced dynamics, perhaps structured ejections, as though the core is pocked with nozzles or outlets directing vapor and grit outward in targeted, powerful bursts, all emerging from a nucleus whose skin is scarcely sufficient to explain the detected emissions. Basic physics requires at least 8% of the surface to be active just to align with water output rates, while carbon dioxide levels imply far more intense releases. Dust elevation theories propose that CO2 blasts are hurling tiny submicron ice particles into the haze, where they evaporate distant from the center, sustaining the envelope's immense span. Such a process is seldom witnessed on this magnitude. The disproportion is tough to exaggerate. A rock the size of a metropolis cloaked in a gaseous layer that overshadows P-planets. Gas emissions surging beyond predictions by magnitudes. Chemical signatures evoking formulas from distant star systems. At present, the data serves as its own alert. Whatever defines 3I/Atlas is appending the fundamentals of cometary science, 1 kilogram of carbon dioxide at a time. Color principles aren't meant to unsettle stargazers. Yet by September 16th, the spectral readings for 3I/Atlas demanded a fresh evaluation. A peak at 518 nanometers, right in the core of the green band, pierced the interference more acutely and prematurely than any simulation had anticipated. Observations from Gemini South first captured the surge in photometrics. The data processing handled that week by Catalina Hernandez marked each exposure with a caution flag. In her confidential message to peers, she noted, "The green band sliced across the pre-dawn heavens like an unforeseen chemical flare, atypical for this solar distance." The shade wasn't faint. Eyewitnesses from 3 continents noted the identical strange radiance, frequently calling it otherworldly, nearly charged. For experts in comet composition, this tint signals C2, diatomic carbon, illuminated by solar ultraviolet rays. Typically, comets reserve their green display for the inner solar realms, the color emerging only when sunlight disassembles organic compounds. In this case, the phenomenon emerged several weeks sooner than projected and with a vigor that challenged established guidelines. Hernandez's group quantified the emission line strength and discovered it matched the most luminous comets on record, despite Atlas remaining distant from the sun's heat. The basic rationale appears straightforward in theory. C2 fluorescence arises from carbon-bearing substances released and activated as the comet warms. The challenge lies in the schedule. Projections drawn from years of comet observations forecast a steady buildup. Expect the C2 lines to climb as the core surpasses specific heat levels. Atlas disregarded the pattern. Spectral data from sites in Chile, Poland, and Hawaii all revealed the identical premature peak. The green signal breaking through ambient static with unmistakable clarity. Hernandez urged restraint, sharing unrefined and refined visuals alongside each other, emphasizing potential for instrumental glitches. No phantom pursuits here, she cautioned. Yet in this domain, illusions can mimic reality. Nevertheless, agreement solidified. The green proved inherent, no optical deception. The comet's envelope, already expanded to planetary proportions, now sported a unique spectral marker distinguishing it from all prior interstellar intruders. Theories ranged from a hyper-concentrated release of carbon chains to alien compositions originating from its remote origin. Every idea deepened the enigma, though nothing fully accounted for the green's premature onset or intense brilliance. The sight mesmerized. Over a handful of evenings in mid-September, the heavens delivered a display that appeared to scorn both remoteness and foresight. The figures narrated a tale of vigor and disorder, of compounds fractured and reformed in the frigid void among stars. But underlying each examination, a query persisted. What sort of body dons an emerald aura prematurely? And what secrets does its illumination conceal? A burst of illumination, keen and oriented toward the sun, divided the comet's sheath shortly after September 9th. Unlike a standard tail, this was an anti-tail, a slender dust beam seemingly directed back at the sun, contradicting the standard principle that comet tails always trail away from solar wind. The optics creating this rarity are uncommon. 3I/Atlas approaches on a backward path almost 175 degrees from the ecliptic, and our planet's viewing angle cuts nearly tangential through the dust layer. For several nights, the comet's particle disk and the watcher's position synced so precisely that grains ejected long ago, trailing well astern, appear to thrust ahead, sunward, via visual slight. It's a brief configuration, yet it transforms the comet's debris into a glowing lance, detectable in long-exposure images from Poland to Chile. Yet the anti-tail merely opens the conundrum. The polarimetry group at Warsaw University, under Dr. Marek Nowak, conducted a scan at a mere 7 degrees phase angle. Their finding, a negative polarization low of -2.7%. In comet research, that's an alarm. Typical comets hover around -1 or -2% at such positions. This reflects fluffy, uneven dust particles redirecting sunlight toward its origin. Here, the figure plunges further, more potently than any contemporary comet, even notorious ones like Siding Spring. The readings imply not mere dust, but an arranged dust formation. Grains structured, possibly oriented, into strands or layers compact enough to polarize light exceptionally. What might shape such alignment? The composition provides a hint. Atlas's surroundings brim with carbon dioxide, a gas prone to fueling explosive jets and ejecting tiny submicron particles outward. Should the venting route through cracks, openings, or even electric fields within the envelope, debris might funnel into unified flows, each functioning as a small polarizer. The observations from the Warsaw Group, when aligned with hobbyist photos from that same period, reveal that the anti-tail's luminosity and polarization reach their zenith simultaneously, suggesting a shared source. The phase angle plays a crucial role here. With the sun at just 7 degrees, its rays skim across the particles nearly edgewise, amplifying the backward scattering phenomenon to its fullest. Such a steep negative polarization value of -2.7% marks the signature of highly porous clusters, those formed in the frigid, shadowy voids between stars. Yet the sheer depth of this reading ventures into unexplored realms. No comet originating within our solar system has ever displayed such a profound dip alongside a dust ejection so precisely structured. For now, the anti-tail remains an enigmatic symbol, a clear indicator that the particles encircling 3I/Atlas form not a haphazard haze, but a pattern that's intentional and refined. Is this arrangement born from the inherent dynamics of cometary evolution, or does it signal artificial design? That's the lingering puzzle, with each fresh observation underscoring a configuration that's as elegant as it is disquieting, a stellar arrangement resistant to simple interpretation. October 3rd, 2025, stands out boldly on the agendas of all mission coordinators. That date marks when 3I/Atlas glides by Mars at 0.19 astronomical units, roughly 28 million kilometers away. Amid a packed schedule of cometary and asteroidal flybys, this represents the sole interstellar interloper coming within reach of any world. The chance is extraordinary yet brief. The spacecraft circling the red planet, Mars Reconnaissance Orbiter, CASSIS aboard ExoMars Trace Gas Orbiter, HRSC on Mars Express, confront a complex array of choices. Leaked internal correspondence, later cited in ESA announcements, paints a picture of internal conflict. Research groups pushing aggressively for optimal captures. Control crews assessing the hazards of abrupt maneuvers. The trajectory of the intruder refreshes nearly every day, offering scant margin for mistakes. Each probe grapples with unique limitations, orientations of solar arrays, transmission capacities, buffers for equipment protection. The timeframe for snapshots spans mere hours rather than days. The backdrop is a celestial arena in frenzy. Late in September, 414P/perihelion hurtles toward its closest solar point. R2 Swan grabs attention with its own near miss of Earth. A 6 Lemon heads in for a November solar graze, as a flurry of small asteroids navigates the inner realms. This creates a form of priority rationing for views. Oversight leads face tough calls, allocate vital assets to a comet appending established norms, or adhere to planned sequences and potentially overlook a landmark occurrence. In the shadows, tension builds. The cluster of celestial bodies filling the fall heavens only amplifies the stakes. Every potential target gets balanced against the uniqueness of 3I/Atlas, its origins from beyond, its coma rich in CO2, its track record of appending forecasts. Timetables get overhauled. Standard imaging plans, typically set far in advance, get scrapped and reassembled in the dead of night. The strain on operations is tangible. Every tweak risks lost readings or, at worst, breaches in hardware safeguards. Still, the potential rewards are compelling. No red planet satellite has previously imaged an interstellar comet at such proximity to a world. The insights, if obtained, might resolve queries on particle makeup, vapor release, and core mechanics of these extraterrestrial arrivals. As October 3rd draws near, the feeling of one irreplaceable shot intensifies. The heavens teem with action, but for those fleeting moments, every lens, robotic and mortal, fixes on a single entity. The results won't merely plug a void in a bustling era of findings. They'll shape the future of how we in planetary studies react when the universe unleashes an unpredictable new era. To gauge the oddities of Comet 3I/Atlas, researchers draw on its two interstellar predecessors as reference points. 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Each reshaped aspects of our field, though through profoundly contrasting paths. Oumuamua emerged as a mystery. Lacking any envelope or streamer, its brightness varied with spins but showed no emissions. Its solar voyage deviated faintly from pure orbital mechanics. Nuanced, enduring, and unresolved to this day. Borisov, on the other hand, embodied the ideal interstellar wanderer. Its emissions and particles obeyed conventions, powered by water and carbon monoxide, with luminosity patterns aligning to blueprints for local comets. The figures aligned. The principles stood firm. Cautious after past surprises, experts shaped projections for 3I/Atlas around these models. They equipped analysis streams with tools refined by Borisov's reliable surge and Oumuamua's enigmatic quiet. Anticipations included a luminosity increase tied to solar proximity, an expanding envelope synced to heating, emissions tracing a standard, foreseeable path. Tracking arrays from Earthbound scopes and orbital observers stood ready to detect any shift from Newtonian paths, mirroring the intrigue of Oumuamua's peculiar nudge and Borisov's archetypal norm. The initial phase of monitoring aligned well with predictions. Preliminary light measurements indicated a subtle increase, perfectly aligning with standard comet simulations. Teams from JPL, ESA, and Harvard conducted thrust evaluations and detected no evidence of unusual forces. The object followed its hyperbolic path accurately, with orbital calculations needing no adjustments. Briefly, 3I/Atlas appeared reminiscent of Borisov, a visitor from afar, yet adhering to expected norms. That changed in September. The sudden surge in brightness, the expanding envelope of gas and dust, the spectrum rich in CO2. Each fresh observation pushed the limits of conventional models. Researchers at the Minor Planet Center and the ENIO Coordination Center pored over motion records, hunting for traces of the Oumuamua MUA phenomenon. Nothing emerged. So far, the path holds firm under gravity alone. The oddity, evidently, lies in its composition, reactions, makeup, and emissions, not its movement. What was once a reassuring standard now highlights the enigma. Indicators suggest not a fleeing body, but one with internal processes unlike any previously documented in the field. Without clear signs of non-gravitational influences, attention turns to its chemical makeup and particle emissions, where true irregularities and potential explanations reside. Rumors flourish amid sparse details. Theories posit that 3I/Atlas could transcend mere comet status, a veiled probe, engineered relic, or intentional emissary from a distant system. These notions rest on three key aspects. Firstly, the gas envelope, led by carbon dioxide rather than water ice, hints at propulsion fueled by an exotic source. Proponents claim CO2 serves beyond mere evaporation. In optimal setups, it acts as thrust material. This isn't mere fantasy. Solar warmth can trigger CO2 outflows. Theoretically, a design optimized to capture and release this substance might enable steering or, at minimum, control over its visibility. Secondly, the polarization readings. The Warsaw Group's finding of -2.7% at a 7 degrees phase angle marks the lowest dip for any recent comet. Online commentators hail it as clear evidence of structured particles or synthetic fibers. Experts counter with lab simulations, noting that rapid, irregular grains, particularly if electrified and oriented by fields in a CO2-heavy atmosphere, can yield comparable results. The evidence is tangled, yet the hypotheses are neat. Structure amid expected disorder, a form suggesting purpose. Thirdly, the information void. Absent photos from September and quiet from leading facilities have sparked countless conjectures. Does this lapse stem from routine solar positioning and timetables, or from controlled disclosure? Social media voices portray it as deliberate, a veil dropped precisely when intrigue peaks. Researchers, however, reference the familiar hurdles that plague every solar approach: protective protocols, processing delays, and the unyielding layout of the inner system. The Fermi paradox lingers subtly. If life abounds across the cosmos, why not blend in with cosmic rubble? Why not embed a device within the clutter of icy wanderers and rocky fragments? The crafted hypothesis captivates: CO2 for concealment and drive, polarization as subtle messaging, the silence as intentional restraint. Still, every assertion teeters on feasibility's brink, always outpacing the facts. Currently, observations confirm only the visible, an interloper defying comet conventions without violating physical principles. Everything else mirrors our drive to find purpose in cosmic quiet. Hubble's July images stay available, and the August 6th JWST spectral data cleared processing swiftly. Yet as the object's luminosity and actions escalated wildly, the flow of shared updates slowed. No updated HSD or JWST visuals surface in records for September. Gemini's typical open calendar lacks bookings for 3I/Atlas in the pivotal period when illumination veered off course. The body solar separation, a safe 45 degrees at August's close, drops to 30 degrees by September's end. For HSD and JWST, such figures impose strict limits. Threats to instruments and circuits brook no compromise. Even earthbound scopes, bound by their rise times and dim skies, encounter narrowing opportunities as the comet edges toward the sun in morning twilight. Volunteer observers keep sharing readings and brightness data, but premium, detailed spectral info from premier sites vanishes from open access. Communication teams, vocal in July and August efforts, issue no fresh statements. The concern isn't intrigue, but oversight. A celestial body appending comet norms, right when elite observers must avert their gaze. For followers of the saga, September's data scarcity underscores a truth. At times, the cosmos' most compelling developments unfold beyond our view. Behind the veil of everyday protocols, regulations, and orbital mechanics, significant celestial occurrences each carry their share of uncertainties. Yet C/2023 A3 Atlas has pushed predictive analysts into extended hours and troubling projections. The information scarcity during September represents more than a mere setback. It's an interval in which the comet's most erratic actions might occur without detection. For experts dedicated to assessing unlikely events, this period sparks hypothetical explorations. Imagine the core breaking apart while concealed by solar glare. Could an abrupt flare, undetected from our planet, subtly shift the trajectory enough to modify the Mars encounter or dispatch fragments along novel routes across the solar system? The calculations prove both cautionary and captivating. A velocity change of 5 kilometers per second from one intense eruption might transform a remote skim into a collision with Mars. This isn't a prediction, merely a sensitivity analysis, a gauge of how minimal an influence can reroute the star's gamble. Gradual splintering, with icy fragments detaching steadily, might manifest as subtle recurring glows. If only premier observatories weren't blinded by the sun's radiance. No such indications have been verified, though lack of proof doesn't equate to proof of non-existence. The comet re-emerged into view by late November, and its nearest Earth passage at 1.88 Australian dollars on December 19th will provide the initial opportunity to scan for fragment streams, recent ejections, or minor trajectory shifts. While the general audience seeks clarity, researchers exchange cautious updates via private discussions and confidential reports. The terminology remains precise. Risk interval. Look for signs of breakup. Track small-scale ejections. The implications concern knowledge, not catastrophe. What escapes notice in this obscured phase isn't security, but the chance to observe an uncommon visitor from beyond reshaping our cosmic guidelines. The foundational observations endure. A brightness pattern that defied expectations, an escaping CO2 envelope, and dust scattering that defies conventional theories. With the obscurity persisting, forecasters continue their models, aware that the ensuing developments hinge on cosmic disclosures. On September 14, 2025, the Minor Planet Center noted a +1.6 magnitude spike in the object's luminosity, prompting worldwide attention. Spectral analysis quickly uncovered a CO2-rich envelope spanning over 700,000 kilometers around a core under 2.8 kilometers in diameter. Baffling polarization values reaching -2.7% at a 7 degrees phase angle elude existing comet theories. Even with public photos from HSD, JWST, and Gemini up to late August, September's datasets grew limited, attributed only to data exclusivity periods and viewing constraints. No non-gravitational forces or emissions have been detected. As C/2023 A3 Atlas swept by Mars at 0.19 Australian dollars on October 3rd, much of its solar closest approach stayed eclipsed by the Sun. Regardless of whether its peculiarities stem from exceptional natural processes or enigmatic sources, the accumulated data highlights a genuine void in our comprehension. As fresh observations surface post-conjunction, resolutions, if forthcoming, will derive from tangible sightings, not speculation.